Hi, my name is John Min. I'm here to give you a quick demo and performance of our Andes NX27V vector processor. So let's get started with the overview of it with Vector Processor Core. We built our NX27V as a RISC-V 64-bit GCN core plus Andes proprietary V5 performance extensions. And then the real star will implement RISC-V vector extension. We built this core on top of our proven 5-stage pipeline, single-issue scalar core with a great branch prediction that's optional. Then, because Vector Unit is a high-performance compute engine, we spend a lot of time moving data in and out of the core with the caches available and with hardware underlying loads and stores, optional parity or ECC protection of those memories. Then these caches or bus interfaces are improved, the instruction and data prefetch, and 16 outstanding data accesses. This is high performance memory system that feeds the VPU by standard RISC-V vector loads and stores and streaming ports you built using our Andes custom extension to accelerate loads and stores as well. Let's look at the vector processor in more detail. Our vector processor supports RISC-V Vector 1.0 spec. We support all the data types from integer and floating point, and we added two more data types, bfloat16 and int4. Now, our vector processor is very configurable from 512 bits all the way down to 120 bits, depending on your area, power, and performance budget. Our vector instructions are started after it's retired from the scalar pipeline. There are multiple functional units that operate out of order independently for the maximum performance and throughput. All the instructions are chainable and mostly fully pipelined. Again, there's two ways to load data in and out: standard RISC-V vector loads and stores, and ACE and its custom extension streaming port loads and stores. Let's look at our streaming port a little bit in detail. A streaming port is a dedicated port created with Elmo aware to communicate with external accelerators and memories. It is controlled by custom instructions in the ACE pipeline. So, quick example, maybe I have a frame buffer specific memory that resides off core that needs processing. We could use the streaming port to bring that data in for vector processor to process and then stream the data out. It's a dedicated port, doesn't steal the bandwidth from main system bus. This gives you high performance because hardware engine is now very tightly coupled, no data congestion. Now, a little more detail. What does this mean in the performance? Well, I still have this scalar processor executing instructions. So I have one pipeline. Second pipeline, I have a vector processor unit executing vector instructions with the data that's loaded from the stream port. Lastly, I have an ACE pipeline, Andes custom extension pipeline, executing instructions to that tightly coupled coprocessor and memory. I could have 3 different instructions in flight at the same time. Very powerful extensions. So what does this mean in terms of PPA? Well, it depending on what you wanted to implement, what kind of hardware budget you have and performance requirements you need. For your hardware budget, one of the larger sizes, you'll be looking at about 2.5 million gates. Now, with the smaller sizes, you could go down to 1.2 million gates for 256-bit implementation and well below million gates for 128-bit implementation. So that's what the hardware implications are. Let's see what the performance implication is. So 512-bit SIMD doing a floating point 32 add, I could accelerate it about 35 times over standard RB64 instruction set. For floating point 32 gem, acceleration is 60 times higher, and some of the CNN functions performance gain could be about 150 times higher. So this is a very high performance engine. Of course, if you have a smaller SIMD implementation, then your performance gains might be a little less. But even at 256-bit implementation, performance gain could be up to 80 times or even higher performance gain. So how do we optimize the software? We're CPU, so software needs to be optimized. We have a tool called AndeStar that works with our simulators to look in the pipeline of the core to identify load-to-use penalties, stall conditions, branch misprediction, so that you can go down to assembly level to really optimize the code to get you the 100% performance you're looking for. Very powerful tool. As for a demo. Now let's look at the real-time performance. We know what the smaller algorithm performance gain is, somewhere between 40, 20, 50 times. What's a real-life example performance? We're going to take a MobileNet, and we're going to run it with the standard RISC-V 64-bit instruction set. Then we'll look at the data from the DSP instruction set, and then vector instruction set. So let's go. So we have the same platform. It's a FPGA platform with our NX27V. Since this is a processor, we run a pure C code, and then we end up with about 55 billion cycles. So it took 55 billion cycles to run this MobileNet code. If my processor ran at 1 gigahertz, it'll take you 55 seconds. Now, so we're filling the table, and we also did it for DSP, and we had 4 billion cycles. So DSP P extension acceleration is about 10 to 15 times. Now let's look at the vector. This is very interesting. And this is using 256-bit vector. So we run it again, and then we end up with 1.4 billion cycles. So acceleration is about 40 times. So vector unit accelerates MobileNet application 40 times over standard RISC-V 64 instruction set. If I use the 512-bit implementation, it'll be much lower, but it doesn't fit within the FPGA. So I hope this gave you a quick overview of NX27V, some of the performance gains you can look for, and what the real-life achievements are. Thank you very much.